Hello. Today we are going to have some discussion about theoretical aspects of the estimator. So we need some preliminary theories for to study the estimation results. And in the previous lecture, I have explained two principles of estimation and also some examples, some familiar examples of estimators like MLE, least squares, or GMM, or least absolute deviations. And then the conclusion from the last lecture was that what we need is the sampling distribution. So, simply speaking, we would like to study the distribution of the estimation error. So there must be some estimation error, even though we cannot control that, we cannot remove that, and we cannot observe what is the estimation error. But theoretically, we can derive the distribution of the estimation error. So from the sampling distribution, we could calculate like standard error, p-value, confidence interval, or and also we can show that your estimator is unbiased, consistent, and like efficient, and your hypothesis testing has satisfies the size, blah blah blah. So all those things are coming from just one object, the sampling distribution of the estimator. So the final goal of this chapter is to study the sampling distribution of a general class of estimators. And so we need some preliminary asymptotic theories. And I believe you learned those theories earlier in another class. And I'm going to review. I will, as I said, I'll try to give you as easy as possible, as easy explanation as possible. So I will give you more like intuitive and simple examples, and which will be used later. Okay, first, what you need to understand is the norm. So the two vertical bars stand for norm. You can interpret this as a generalization of the absolute value. So when you have a scalar, if v was scalar, then it equals to the absolute value. But when v is a vector, then the norm becomes this form. But still, you can interpret it in the same way. Basically, it is the distance from the origin. That's the definition of the absolute value of a number, and we do the same thing. And when we say the vector is bounded, or a random vector is bounded, when it satisfies this. So all the possible values lie within a certain distance from the origin. So it does not go too much far away from the origin. So that's the definition of boundedness. And a very common inequality you need is the Cauchy-Schwarz inequality, which will be applied in many places. Like you can interpret it as covariance and variance and variance. The Cauchy-Schwarz inequalities have many variants and many possible interpretations in many different fields. So I recommend you to search for Cauchy-Schwarz inequality on Wikipedia. Then you can find some applications and examples. And the Cauchy-Schwarz inequality is used also commonly used in statistics and econometrics. Okay, and next for matrix, the inverse matrix is the matrix you know, and simply it is the generalization of the reciprocal of a number. 1 over m, if m was a number, then it is the inverse of the number. And for a matrix, we write it this way. And as so even when it is a number, you need to assume that the denominator is not 0. So the same thing, similar or general similar assumption is required for a matrix too, which is this. The m should be non-singular. So when m is singular, you can understand it as the matrix equals to 0. More rigorously, if the determinant of the matrix is 0, then the matrix is singular. But if you know what is the determinant, that will be good, but you don't need to. As you can imagine, so if suppose that if a sequence converges to a number, and if the limit is non-zero, then for sufficiently large n, the sequence will be non-zero. So when the sequence is converging to m, a point which is different from 0, then if after a huge convergence, it has to be close enough to the point. So at that point, it should be different enough from 0. So similarly, if the limit is non-singular, then the sequence will become non-singular for a large number of n. First, several matrices during the sequence could be singular, but after many iterations, when the convergence has been in progress for many times, then it will be non-singular. So that's parallel to the scalar case. And let's think about theta, which is a vector, and g is a function of the vector. So, but g is mapping from k-dimensional vector space to a one-dimensional real number. And in this case, we still need to think about the differentiation. And differentiation is written in the same way, but this is a vector. In that case, the derivative is also k-dimensional vector, because you have to differentiate. So theta is a vector, so the function depends on k different arguments. So its derivative has to be calculated for each of the arguments. So there must be k different derivatives, and they will be written in simply this way: k-dimensional vector. And if you transpose in the denominator, then it's equivalent to this guy. So think about this. So the second derivative is k by k matrix like this. So the first derivative is k-dimensional function, and then you need to differentiate once more after transposing this. Then you get k by k matrix. So it's simple. And also, even if the function was a vector, then you can differentiate. However, now you have to use transpose here, because already the numerator is m by 1 vector, and so you have to make the denominator as 1 by k. So the result is m by k matrix. It is just a standard notation. And in this case, a vector function case, the second derivative requires a three-dimensional matrix, which is not possible here. So it's not convenient using this notation with second derivative. And when we say the function is continuously differentiable, then it means that the derivative is continuous. So it means that the function is differentiable everywhere, and second, the derivative is continuous, right? Okay, that's a simple notation about vector matrix and calculus. And next, I'd like to talk a little bit about convergence rates. It's very confusing. I remember when I was a student, I don't understand why we are using this notation. So let me clarify, give you the intuition. So I will do that in the next video. So see you later.